So we have finished circular motion. Now we're going to move on to the next PowerPoint, aero drag or resistance. We have been ignoring aero drag for all the problems we have discussed, right? But now we're going to study aero drag in a little bit detail, because we know that for certain things, like a tennis ball, you should consider aero drag when it's falling. It's not going to be in free fall because the aero drag is going to be comparable to its own weight. All right, and what is the theory for aero drag? Well, again, the aero drag is a very complicated topic as friction force. We only have an empirical equation for that, but this empirical equation can help us make predictions at a very good degree. So in macroscopic physical system, so that's a very good theory. So this is the equation: 1/2 CD rho A V squared. So there are many symbols here. What are these symbols? CD is called, C sub D is called drag coefficient. So the dimensionless number, it's like the mu S or mu K, that's the coefficient. Rho, this Greek letter rho, is the density. So if it's falling in air, that's going to be the density of air, right? A is the area, and in this case, it's the cross-sectional area. Should be careful. It's not the whole area of this falling object. It's only the cross-sectional area. And V, it's the normal V, the speed. Okay. So as I said, take a look at the second slide. If something's falling, the A you plug in, it's only going to be the cross-sectional area, not the whole area of the object. For example, if a sphere is falling, you only need to calculate the area of a circle. You don't need to calculate the whole area of the sphere, which is going to be, if you still remember that, the area for a sphere is 4 pi r squared. But the cross-section area is just going to still be a pi r squared. You still use the cross-section, the area of a circle. If a cylinder or a box falling, you only need the area of the base. Right? If it's a cylinder, it's still going to be a circle because the base is a circle. And if it's a box, you don't need the whole area. You just need the area of the base. Okay, so that's one thing you need to be aware of. It's the cross-sectional area, not the total area. Now let's take a look at two questions. I want you to use these two questions to understand why for certain things we don't need to worry about a drag. But for other things, we do need to worry about that. We do need to include them when we study their motion. Let's take a look at the first question in slide 3. A baseball is dropped from the top of the Empire State Building. Please don't do this experiment. The baseball has a radius 3.74 centimeters. And a mass 0.15 kilograms. Okay, we have the radius and mass of this baseball. What do we want to find? Find the acceleration of the baseball with air drag when the speed of the baseball is 20 meters per second. And the drag coefficient 0.3 given. Air density is 1.2 kilograms per cubic meter, so SI unit. Now let's see. If the air drag is on, you don't ignore the air drag. How many forces are on this baseball when it's falling? Well, you would draw still gravity on it, and the air drag, it's going to be in the opposite direction. Right? The air drag is like a friction force. It's going to slow it down. Then how do you find the acceleration of this ball? In this case, obviously when it's falling, the acceleration is still down. Right? The acceleration is still down. So I have two vectors down, one vector up. So to avoid negative signs, let's just call this guy down positive direction, okay? Because at the end, the acceleration I find is going to be a positive number. Now let's do that. If I call the down as the positive direction, I want to find acceleration in y direction. That's just going to be net force in y direction divided by the mass. I do have two forces in y direction, and in this case gravity is larger, right? And the gravity is positive, so I would do gravity minus the L drag divided by the mass. Now I do have the mass from the problem. The mass of this ball, it says it's going to be 0.15 kilograms, right? And I have the radius of this ball, 3.74 centimeters. You can convert it to meters. So if I want to find the acceleration, I just need to plug numbers into this L drag equation and then find the number, and then I can find the acceleration. Okay, so and then you do have all the numbers you need, right? The problem says let's use this coefficient 0.3, the density of air is 1.2 kilograms per cubic meter. All right, so pause the video, go ahead and finish the algebra. Okay. So what is the L drag you get? In this case, the L drag is just going to be 1/2 CD rho. The A is going to be pi r squared because it's a sphere. Remember, it's sphere. You only calculate the cross-sectional area, which is still going to be a circle. And the V, what is the V? So the problem says I want to find the acceleration when the speed of the baseball is 20 meters per second, right? So you do need to know the speed. So actually, the L drag changes with the speed. So this is very interesting. We're going to see. It's going to actually cause this guy to have a maximum speed when it's falling with the L drag. But anyway, you put all these numbers in carefully, convert this radius to meters, because you can't use centimeters. You have to make sure everything is in SI units. What is the L drag you got? The L drag I got is 0.316 newtons. All right, so now you can plug all these numbers into this Newton second, rearrange Newton second. What is the acceleration you found? The acceleration I found is going to be 7.7 meters per second squared. So for baseball, because it's very light, the L drag is comparable to its own weight. When it's falling, you do need to consider L drag. Otherwise, you're not going to get the right answer. Because when a baseball is falling, it's definitely going to be slowed down by the L drag. It's not in free fall anymore, right? 9.8 is the free fall acceleration. So for things like baseball, you do need to consider L drag when it's falling. Otherwise, you're going to make a wrong prediction. Take a look at the next question. A copper ball. Now we're going to replace the baseball with the copper ball. Dropped from the top of a state building, okay? The same experiment, but please don't do that. The copper ball has a radius, the same radius, but the difference is the mass, right? For the copper ball, the only difference, the mass is going to be a little bit heavier. Of course, it's a copper ball. If the copper ball has the same size with the baseball, it's definitely going to be heavier. So the mass is 2.8 kilograms. But that's the only difference between these two questions, right? The radius, we make them the same size. The coefficient is still 0.3. The density of air is still 1.2 kilograms per cubic meter. I still want to find the acceleration of the copper ball with L drag when the speed of the ball is 20 meters per second. So everything is the same, only this is different. So the acceleration is still going to be, because the free body diagram is going to be the same, right? Doesn't matter if it's a copper ball or baseball falling. Gravity down, L drag up. Acceleration is still down because it's falling, right? And then you still rearrange this Newton second. Now you can plug in all the numbers to find the acceleration for the copper ball. So the L drag, you should calculate it, right, for the copper ball, but it's gonna, because you have all these same numbers, so the L drag for the copper ball, you don't need to calculate again. For this part, it's going to be the same number because the problem gives you the same parameters as the baseball. All right, so pause the video, put all the numbers in, find the acceleration when the copper ball is falling with L drag at 20 meters per second. All right, so what is the acceleration? As I said, the L drag, because you get all the same numbers, so this number is still going to be the same on this copper ball. You plug this L drag in, the acceleration you found is this. So 9.7. Well, it's a little bit lower than 9.8. I know the free fall acceleration is 9.8. But this is the difference is like a 1%, right? Around 1%. So for things like a copper ball, right, in our life, you drop it, then and normally it's not going to reach 20 meters per second unless you drop it at very high, right? So even at 20 meters per second, that's actually very fast, okay? That's actually a very fast speed. Even at 20 meters per second, the acceleration is still very, very close to free fall. So in everyday life, like things like a copper ball dropping, okay, falling under gravity, and air drag, even if you consider air drag, it's not going to make much a difference. So for things like a copper ball, we can just ignore the air drag in real life if we want to make a prediction. But for baseball, no, you cannot, right? Because you see, there's a huge difference between this number and the free fall acceleration. So baseball falling with air drag is definitely not in free fall. You shouldn't use free fall. Copper ball, well, if you use free fall, you're not going to get much of a difference. Okay, you're going to still get a very good prediction. Okay, so that's the reason for things like baseballs or a piece of paper, of course, you cannot ignore air drag. When they're falling, the acceleration is not going to be 9.8. Okay, so that's the difference between them. Now let's see. Now we're going to talk about the because when something's falling with air drag, so it's not a free fall anymore. So the velocity actually behaves very interestingly. It's different than velocity in free fall. When I ask you how does the speed of an object change in free fall, that's very easy. You would just say, well, when it's falling, as long as it keeps falling, the velocity keeps increasing because the acceleration is always 9.8, right? So 9.8 is just the rate of change in the speed. So as long as it still keeps falling, the velocity is always gonna increase 9.8 for every second. So very easy, okay? Nothing really surprising. But when something's falling with air drag, it's different. Okay, the difference is this. I know that the acceleration of this thing is going to still be, if I want to find how the acceleration and speed changes, think about it. When something's falling with air drag, this is the net force on it. Net force divided by mass is going to be the acceleration. Okay, so if the air drag is on it, it's comparable to the gravity. This acceleration is going to be smaller than free fall, but it's still going to increase. Okay, but it's not going to increase with the same rate. So that's the interesting part, because once it has some acceleration, say this number, so next second, so the acceleration should get larger a little bit because it's accelerating down. It's still accelerating down. But when the velocity gets larger, what about this guy? This guy also changes because the air drag also changes with the velocity. So the next second, the air drag is going to get a little bit larger. If the air drag gets a little bit larger, how does the acceleration change, right? Air drag is here, so if air drag gets larger, what about the acceleration? And the acceleration gets smaller or larger, and that's also going to affect the motion of this object at the next second. So this is the question I want to ask. I want to ask you. Take a look at the question on slide 6. So at the end, after you consider all these factors, when something falls from rest with air drag, okay, from a very tall building, how does the speed change? Okay, at the end. How does the speed change at the end? So think about it. Which one is the right answer? There are 5 answers here. How does the speed change? If you consider all the factors, the change of the acceleration, the change of the air drag, so how does the speed change at the end? All right, what is your answer? The answer is going to be C. It's going to first increase, then remain constant. Okay, so this may not be that intuitive. You're going to draw it out, use Newton's second law to help you figure it out. Okay, so now let's see. I know that at the beginning, so it starts from rest, so the velocity only going to be a very, very small number, right, when it's falling. So I would have something like this. Gravity down, the air drag is going to be very small. Acceleration is going to be this value. So acceleration is going to be a little bit smaller than 9.8, but it's still some value and it's down. But if it has an acceleration down, so it's accelerating. So the next second, the velocity is going to get a little bit larger, right? It's falling and it has an acceleration down, so it's accelerating. So next second, the velocity gets a little bit larger, and then the acceleration, I'm going to draw it down. So the L drag is going to get larger. So the next second, if you draw the free body diagram, you actually draw it this way. Gravity is still down. L drag is going to get a little bit larger. So, but still, at the very beginning, the L drag is still going to be less than gravity, right? So it's falling. You still have an acceleration down. And the velocity is still going to increase the next second, but the rate gets a little bit smaller, right? For example, in the first second, the velocity is going to increase by 8, but then because the L drag gets a little bit larger after that, so the next second after this, the velocity is going to get larger by 7. It's going to increase by 7, right? But still, if I have an acceleration down, the velocity is going to keep increasing, but the rate gets smaller and smaller, okay? So, and then what about the next second after this? Next second after this, because the velocity gets larger, so this guy is going to get larger even more. So you will have a gravity, you have a normal force. So the normal force is catching up with the gravity. Okay? So it's going to keep increasing. But at this second, if this is still a little bit smaller than gravity, you still have an acceleration down, and it's still falling down, so the velocity is still going to increase a little bit, right, after this, until if it keeps falling, at some point you will have this. Gravity down, and then the normal for the L drag is going to get as large as the gravity. So at this point, if at some point the L drag gets as large as the gravity, what is the acceleration of this object? Well, these two forces, if they are the same, and then in opposite direction, they should cancel out exactly. So the acceleration at this point is going to be 0. If the acceleration becomes 0 at this point, how does the velocity change after this point? If the acceleration becomes 0, the velocity doesn't change, right? Because what is the definition of acceleration? Change in velocity divided by change in time. But if acceleration has already become 0, then there will be no change in velocity. So velocity is going to stay a constant after this point. And if the velocity stays a constant after this point, L drag is going to stay a constant after this point. And L drag stays constant, so L drag is going to be always equal to gravity after this point. So acceleration is going to be always 0. And then that's going to make the velocity always constant after this point. So after this point, if it's still falling, then nothing will change. There will be no change at all. This is going to be the simplest motion. Something moving with no zero net force on it, constant velocity, uniform motion, right? So if you take a look at the change of the velocity, it's going to increase. It's going to reach a maximum at this point, and then it's going to stop changing. So this is the maximum velocity it can get, okay, when the L drag becomes as large as the gravity. Okay, so that's how the velocity changes. It's going to first increase, but at some point it's going to reach the maximum, and after that point, it's going to remain constant. All right, so that's what we call terminal speed. That's just the maximum speed it can get when falling with L drag. And then we can actually find the equation for the terminal speed by making use of this condition. Because I know that the maximum speed, the terminal speed, occurs when drag force L drag equals gravity. So Now, what is the equation for L drag? L drag is going to be this: 1/2 CD rho A V squared. So if the velocity has reached the maximum, the terminal speed, these two numbers must be equal. You see that you rearrange this equation, you will get a very nice expression for the terminal speed, which is the maximum speed this object can get. Okay, some of you may have already heard about this term, terminal speed. All right, and this is not something I don't need to remember this conclusion, right? As I said, physics is not about memorization. It's not about memorizing stuff. Once you have this equation and you understand why there is a maximum velocity and when does this maximum velocity occur, that occurs when the L drag becomes as large as gravity. So nothing is going to change after that. You use this equation, you set this up, you will find the expression for the terminal speed. That's what we're learning in physics. I want to understand this whole process and understand how we got this. Okay, I'm not going to remember this expression. Of course, you will get this equation on the test. You will get all the fundamental equations you need in physics. You don't need to worry about equations. If you always worry about equations, if you're always trying to memorize equations, you are in the wrong direction. Physics is not about memorizing equations. Physics is about understanding the laws and theories and apply them in different problems. Okay, so and this thing really happens. Okay, this is not just a theory. I've attached a link to a YouTube video where you can see that in skydiving. Okay, take a look at the video. It's a very cool video. If you can measure, okay, if you have a speed meter to measure the speed of this skydiver, so you can see that in that video, the velocity, the speed of the skydiver is going to increase, increase, increase. At some point, it's going to reach a maximum. And after that point, it's going to stay a constant. So this really happens in real life. Okay? It's not just like some theory made up by physicists. And it's just a conclusion from this theory, the empirical theory for the terminal, the L drag. Okay, so next what I want to do is that I want you to compare the falling, the maximum speed the object can get when falling with and without L drag. That's what I want to do next. So let's take, I want you to compare that. Let's take a look at the question on slide 8 first. Calculate the speed at which a 0.15 kilogram baseball strikes the ground if dropped off the top of Empire State Building. I want you to ignore L drag. If I ignore L drag, it's just going to be in free fall. And if you want to find the speed of this baseball when it strikes the ground, you just use kinematic equations, right? Because free fall is a constant acceleration motion. The acceleration is always 9.8. So you can go ahead and pick one, then you're going to pick one of them. And in this case, if you know the height of the building, so that's just going to be the yi and yf. In this case, you know the yi and yf, right? So if this is the ground, this height is 443 meters. So you would call yf 0. yi becomes 443 meters, right? All right? So, and then in this case, which one is the best equation, a kinematic equation? Pick that and then plug numbers in. You can find the speed of this baseball when it strikes the ground. And that is just going to be the maximum speed, because it's just going to keep increasing the speed. Okay? Pause the video, find the maximum speed. In this case, if I know these two heights, the best equation is going to be the third one. The third one has VYF squared equals VYI squared plus 2AY YF minus YI. Right? And then If this is dropped, so Vyi is going to be 0 at the beginning. What is acceleration? Free fall, negative 9.8. If you still call up positive, and then you plug all the numbers in, YF is 0, you will get a negative number here. That's going to cancel the negative sign here. You see that you don't need to erase any negative signs in physics. If you get all the signs right, everything is going to be consistent. Because you're going to take your square root, you can't have a negative number on the right. And if you get all the signs right, all the signs, negative signs, they're going to cancel out. You will get a positive number on the right. So you take a square root, what is the final speed you get? You should, again, you take a square root, you actually get positive and negative value. You don't always pick the positive value. But in this case, okay, so it's just telling you the value is 93.2 meters. What is the direction? Well, you can say down, or I'm just going to pick the negative value. So that's just telling me it has a value 93.2 meters per second, direction is down. Okay, so this is the free fall, and we already know how to do that, right? We learned free fall earlier. Okay, so the second question, the second part of this question, we do want to calculate the speed of this baseball without drag. So the falling of this baseball without drag is actually very complicated, right? Because the acceleration is not a constant. The acceleration actually is going to get smaller, smaller, smaller. So the velocity is going to increase with a smaller, smaller rate, and then it's going to reach a constant and then keep falling after this point. So I cannot use the kinematic equations because this process is not a constant acceleration motion. But if I only need to know, in this question, I only want to find the speed of the baseball when it strikes the ground without drag. All I need to do is just find the velocity at this point, which is the maximum velocity it can reach, and the terminal speed. Because after this point, nothing's going to change. It's just going to keep falling with this speed and then hit the ground. So if I only need, of course, if you want to figure out at what height this is going to happen, it's going to reach the maximum speed. Well, it's going to be a complicated problem, but you can still do that. You can use calculus. You can still find the height. But if in this part we only want to find the final speed it strikes the ground, I just need to find the speed at this point, which is the terminal speed, because after this point nothing is going to change. It's just going to be a uniform motion. And finding this speed, we already know how to find this speed, how to find the terminal speed. Again, you don't need to memorize the terminal speed equation. You don't need people to give you that equation. If you understand that terminal speed occurs when the acceleration becomes 0, the net force becomes 0. So these two forces opposite, they must be equal to each other. So I can just derive that within less than a minute. L drag must be equal to gravity, and then plug this in. What do you get? You will get 1/2 CD rho A V squared equals mg at terminal speed. Rearrange this equation. What do you get? Terminal speed equals 2mg divided by CD rho A square root. In this case, this is the baseball. So the area is still going to be pi r squared. You only need the cross-sectional area. And then you can plug all the numbers in and find this terminal speed, right? And this problem, it says that CD equals 0.3 still, and the density of the air is still 1.2 kilograms per cubic meter. And if you want to calculate the terminal speed, you do need the mass and the radius. You do need the detail of this falling object. So this is different than free fall. If you want to make predictions in free fall, you don't need to worry about the detail of this falling object, because every object falling, they're going to have the same motion. You only need like the height, velocity, acceleration, all right? Things like that. You don't need the detail of the object, but if you want to calculate terminal speed, you do need the detail of this object. The mass, in this case, still 0.5 kilograms, and the radius, you convert it to meters, what do you get? You're gonna 0.0374 meters. Okay, you plug numbers in, what is the answer you got? You can finish this algebra and compare your answer with mine. So the answer I got is 43.1 meters per second. Of course, the direction is going to be down, in this case, if I want you to figure out the direction. And then, now you can compare this value with the value we found in the last part, which is 93.2 meters per second. So this is smaller than 93.2, so that makes sense, okay? Because when the air drag is on it, it's definitely going to be slowed down. You should get a velocity smaller than the velocity you get in free fall. If you get something like 100, you must have done something wrong. Check your algebra, okay? Always try to make sense of your answer. Okay, so this is this question. Now let's use another question, the last question in this part, okay, to practice this theory one more time. Air drag. A skydiver of mass 80 kilograms jumps from a slow-moving aircraft and reaches a terminal speed of 128 meters per second. So I already know the terminal speed of this skydiver. I want you to find the acceleration of the skydiver when her speed is 75 meters per second. Density of air is the same. The CD is 0.8 because now it's a skydiver. Okay, so now let's see. If I want to find acceleration of the skydiver when her speed is 75 meters per second, how do I find the acceleration? Well, that's just going to be like the question we did with the baseball and the copper ball at the very beginning, right? The freeboard diagram is still going to be this. So you're going to still have the gravity down, the air drag up on it, and at 75 meters per second, it's smaller than the terminal speed, so it's still going to be like something like this. The gravity is still larger than the air drag. You set Newton's second law, you still get this, right? Net force divided by mass, you get the acceleration down, if we call down positive. So all I need to do is just to calculate the air drag on this skydiver when her speed is 75 meters per second, because I already have all the numbers I need, right? I have the mass of this skydiver, 80 kilograms. I have the CD 0.8 in this case. The density of air is still 1.2 kilograms per cubic meter. Right? So, and then all I need, so I have a mass gravity. All I need to do is find this air drag at 75 meters per second. So let's see if I have all the numbers for air drag. 1/2 CD 0.8, right? Density of air 1.2 SI units. So I don't have the cross-sectional area of the skydiver, right? I don't have any information about that. The V I plug in is going to be 75. So I'm missing this the cross-sectional area of the skydiver. So what do? Well, you're just going to use some information of the problem to find the area before you do this, right? How do I find the area? Well, we haven't used the terminal speed, right? So I believe that's going to help us find the area. So let's see. Terminal speed. I don't need to memorize the equation for terminal speed. I only need to understand why there's a terminal speed. Because the acceleration, the net force is going to become 0 at this point. Acceleration becomes 0. The velocity is going to become the maximum. And then it's going to keep falling with that speed. So if I want to write the terminal speed condition, I would write it this way. When the air drag becomes as large as gravity, that's when terminal speed occurs. Can this help me find the area? Let's try that, right? So air drag is still going to be this equation, so I'm going to write it down: 1/2 CD rho A VT squared. It's going to be equal to mg, right? Now this VT, the problem says, okay, VT is 128 meters per second. That's the maximum speed that skydiver can reach. Now, I do have mass in little g. I have CD, I have rho, VT, I'm going to plug this number, so I can find the area. Right? So once I find the area by using this information, I can plug it into the same equation again with 75 meters per second. So I can find the L drag at 75 meters per second. That's going to help me find the acceleration of the skydiver when her speed is at 75 meters per second. Okay? So now you can pause the video and then finish the algebra. Now let's see. First of all, you rearrange this equation, find the A, right? But there's an easy way that's gonna make your algebra a little bit easier is this. Because all I need is actually this product, right? The product of the CD rho A, you see that that's what you have in front of this VT squared, and then when you find this L drag, you also need CD rho A. Instead of doing A equals this times this divided by CD, and then I'm going to multiply that by CD to find the L drag for 75 meters per second. I don't need to do that, right? I don't need to divide CD rho A and then multiply CD rho A. I'm just going to find this product. I'm just going to treat this guy as one parameter, right? So that's going to just make my algebra a little bit easier, but there's nothing wrong if you want to find A yourself and then plug it back in, multiply by CD rho. You will get the same answer. All right, so CD rho A in this case, I'm just going to do mg divided by 1/2 VT squared. Now I have all these numbers, plug them in. What is the CD rho A? CD rho A I got is this. Whatever the unit is, it has some unit, okay? I don't need to worry about it. It's going to be in SI units. Now I'm going to use this to find the L drag at 75 meters. You see that I only need this whole thing multiplied by V squared and 1/2. So the L drag at 75 meters per second, it's going to be 1/2. Now I'm going to just plug in CD rho A as one parameter and then 75 meters per second squared. So you see that makes my algebra easier than finding A. So this number I found 269 newtons. Okay, once you have this L drag, you can plug into this rearrange Newton. This is Newton's second law. You can find the acceleration. It's going to be 6.4 meters per second squared. So this is the acceleration of the skydiver when her speed is 75 meters per second. And then it is smaller than 9.8, so which makes sense because when the L drag is on the skydiver, her acceleration is definitely going to be smaller than free fall acceleration 9.8. Again, if you get something like 15, 20, okay, check your algebra. You have done something wrong because with the L drag, you're not going to be even faster than free fall. Okay, so I'm going to stop here for this topic. We have already finished L drag.